All right, problem number 2 in group theory. Let H and K be subgroups of G, and suppose that K has finite index in G. Prove that H intersect K has finite index in H. Okay, so we're going to assume that we have everything that's in the question, and we want to prove that H intersect K has finite index in H. Okay, since K is a subgroup of G with finite index, since K is a subgroup of G with finite index, there exists G1 to Gn in G such that G is equal to the union, display style of the G's, the left cosets with K. Okay, and let's put this in the center, where n is equal to the index of K and G. Okay, so since K is a subgroup of G with finite index, there exists G1 to Gn in G such that G is equal to the union of Gi times K, just the left cosets, the union of the left cosets of K, where n is the finite index of K in G. Okay. We know that H is equal to H intersect K, because K is intersect G, because H is a subgroup of G, so it's a subset of G. Okay, and above we defined what G to be, so we'll grab that definition and maybe we'll go like this. Okay, so we're taking H and we're intersecting it with a union. Well, we can write this as the union of the intersections, like so. Okay. And we claim that H intersect those left cosets is equal to Hi times H intersect K, or before this, I'm actually going to define Hi. I was going to do it after, but I want to do it before. So if that intersection is non-empty, then choose Hi such that Hi is in, we want it to be in H, and we want it to be in Gi, the left cosets. Okay, so if the intersection is non-empty, then choose Hi from that intersection, and we claim that this intersection is equal to Hi times this intersection, which would give us a way of expressing H as a union of left cosets of this intersection, implying that it has index at most n, so less than or equal to n. Okay. So we're going to do element chasing, subset EQ. Let x be in this first guy. Okay. Observe that x and hi are both in gi, the left coset for k, So there exists K1 and K2 in K such that X is equal to GI K1 and HI is equal to GI K2. Then consider we're going to look at HI inverse times X, which is equal to GI K2 inverse times GI K1. Okay, that inverse, we just flip them and we take the inverses of them. So we get K2 inverse times GI inverse times GI times K1. The GI inverse and GI cancel out, giving us K2 inverse times K1. But elements from K are closed because they're a subgroup of G, so this is in K. Hence, we have that HI inverse X is in K. Cool. Further, we have that, let's see, X is in H and HI is in H. So HI inverse times X is in H, again by closure. Thus, okay, we have that HI inverse X is in, well, we showed it was in H, we showed it was in K, so it's in H intersect K. Hence, X is in HI times H intersect K, which is the one way of the inclusion. Now we want to show the other side of the inclusion. Oops, let's do this in, whoops. Do this in math mode. Sup set EQ. Okay, let's make sure this is formatted properly. Okay, and we're going to do this direction slightly different. We're going to let K be in H intersect K and define X to be HI times K. Okay, so why this fits? Well, we want to start with something that looks like HI times H intersect K. K is from H intersect K, so X is HI times something that's H intersect K. So we want to show that X is in H and X is in GI, the left coset of K. Okay. So, since K is in K, and HI is in GI, it's in the left coset of K, we have that X is in the left coset of K. Further, we have that K is in H, and let's see, HI is in H, so HIK is in H, hence X is in H. Therefore, X is in H intersect the left coset of K, which is the other direction of the inclusion. We have the inclusion on both going both ways, thus the claim is true, and these two sets are equal. So we'll say that. Therefore, h can be, say, written as at most n left cosets of h intersect k in H. So h intersect k, the index of h intersect k in H is less than or equal to n. Hence, h intersect k has finite index in H. And we are done with 22.